Welcome to This Explainer. Today, we're unpacking how complex algebra, yeah, I know, algebra, actually acts as a massive toolbox to solve some surprisingly common real-world puzzles. If you've ever wondered how abstract math impacts high-level business decisions or even sports analytics, well, you're in exactly the right place. We are talking about polynomials.
So let's start with a really compelling question. How can a massive business actually cut back on manufacturing, meaning producing fewer items and using way fewer resources while making the exact same amount of money? I know it sounds literally like magic, right? But it's not. It's actually just math.
Let's ground this with a real example. Imagine a shoe manufacturer. Right now, they're producing 1 million shoes and bringing in a very handsome profit of $25 million. But, factory costs are rising, and they really want to reduce their production volume. The catch here? They want to keep that exact $25 million profit completely intact. No pay cuts. So how do they find the precise number of shoes to make to hit that sweet spot? Here's our roadmap for today's explainer. We'll look at real-world polynomial problems, polynomial long division, the synthetic division shortcut, the remainder theorem, the factor theorem, and finally wrap up with real-world math applications. Section 1. Real-world polynomial problems, setting the stage. Okay, so the company's profit, which we'll call P, is modeled by this pretty complex polynomial. P equals negative 21x cubed plus 46x. In this model, x is just the number of shoes produced, in millions. Now, we already know that when x is 1, so 1 million shoes, the profit is 25 million. But since this is a cubic function, it's got a curve to it. It's not a straight line. That means we need to find another value for x somewhere along that curve that also lands exactly on our $25 million target. Moving on to Section 2, polynomial long division, the heavy machinery. Look, to solve a complex equation like that, we can't just guess and check. We need to bring in the heavy machinery, which is polynomial long division. And hey, don't let math anxiety kick in here. This process is actually not that different from the long division you learned way back in grade school. We're just dealing with variables instead of only numbers. You just follow a methodical set of steps, you write it out in standard format, making absolutely sure to include a zero coefficient for any missing powers of x, to hold their place. Then, you divide the highest power term in the dividend by the first term of the divisor, multiply, subtract, and just repeat that loop until you hit your remainder. The absolutely crucial point to remember is this. When you divide a polynomial f of x by a divisor d of x, what you get is a quotient q of x plus a remainder r of x placed over that original divisor. If you think about it, it's the exact same structure as dividing 10 by 3. You get 3 with a remainder of 1. Simple, right? All right, Section 3, the synthetic division shortcut, the math life hack.
So what if I told you there was a way faster way to do this when you're dividing by a simple linear divisor, like, say, x minus 2? If we compare the bulky variable-heavy long division with synthetic division, honestly, the difference is night and day. Synthetic division is this sleek numbers-only shortcut. You literally just drop all the x variables and only work with the coefficients. You bring down the first number, multiply it by your divisor value, add it to the next column, and repeat. It evaluates those coefficients directly, saving you time, space on your paper, and for sure, a lot of potential algebraic headaches.
Section 4, the remainder theorem, the hidden role.
Now that we've got our division tools squared away, let's look at the cheat codes that actually govern them. The remainder theorem illustrates this brilliant mathematical truth. You can find the exact remainder of a polynomial division problem simply by evaluating the function at the value k. Literally, if you're dividing by x minus 2, you just plug 2 into the original equation. The number that spits out is the exact same remainder you would get from doing all that long, tedious division. It is incredibly elegant. Section 5. The factor theorem, finding the zeros. Building directly on that remainder theorem, we get an even more powerful tool. The really interesting part here is the condition if and only if it equals 0. What does that mean for us? Well, it means if we plug a number into our equation and our remainder is 0, we haven't just done a neat math trick. We've actually found a perfect factor. And finding a perfect factor is like finding the key to unlocking the rest of the polynomial puzzle. It lets us take a giant clunky cubic equation and break it down into smaller, much more manageable pieces. As you can see, the factor theorem is incredibly versatile. It basically lets us take one known piece of information, whether that's a given factor, a known zero on a graph, or just an existing solution to an equation, and use our synthetic division shortcut to sniff out all the other hidden answers. It's a real game changer. And that brings us to our final section, number 6, real-world math applications, returning to the toolbox. Okay, we've got our tools. Now let's actually use them to solve that shoe factory problem we started with. Let's walk through this together. Our target profit is 25, right? So we set the equation to 25. To solve it, we rewrite it in standard form by setting the whole thing to 0. Now we already know that 1 million shoes works, meaning x equals 1 is a known solution. Thanks to the factor theorem, we know for a fact that x minus 1 is a perfect factor. So we run our synthetic division shortcut using the number 1, and boom, it seamlessly reduces our massive cubic model down to a much simpler quadratic equation. From there, we just plug it into the good old quadratic formula, which reveals that our second positive solution is approximately 0.7. And there is our answer. 0.7 million. That means the company can dramatically cut their production down to about 700,000 shoes. They save on materials, they save big on factory time, and because of the specific way their revenue and costs curve, they still make the exact same $25 million profit. How wild is that?
But hey, business optimization isn't the only application here. Polynomials and the theorems we use to break them down, they also govern the world of sports.
For instance, look at this. The total historical attendance at NCAA women's basketball games is actually modeled by this complex third-degree polynomial. By dividing this massive attendance polynomial by a simpler linear model that represents the number of active teams, data analysts can accurately predict the average per-team attendance year over year. It lets them adjust for growth in both the fan base and the league size simultaneously. It's brilliant.
So, as we wrap up this explainer, I want to leave you with this thought. From the profitability of the shoes on your feet to predicting the crowds at the sporting events on your screens, polynomials are quite literally everywhere. So what other invisible systems around you are just waiting to be optimized and solved if you only bring the right mathematical toolbox? Keep questioning, keep looking at the data, and we'll see you in the next explainer.